Hi, in this video we introduce the concept of elasticity of demand. In particular, we show why and how it can be used to compare the relative changes in demand and unit price. Since we are going to work with the relationship between unit price and demand of a product, we labeled each of these quantities respectively by P and X. We have seen that these two quantities are generally related through what is called the demand function. So P is a function of X. Letting that function be D, we then write P equals D of X. Typically, demand X increases because the unit price P decreases. In other words, increasing X decreases P, and this makes function D usually a decreasing function. On the following figure is illustrated the graph of a simple demand function that is linear. For example, 100, 500 is a point on the line. This indicates that for a demand of 100 units of a product, your unit price is $500. As you can see, the slope of the line is negative and the function is always decreasing. We use a running example to introduce the concept of elasticity of demand. Consider a publishing company that sells textbooks. The demand function of X textbooks is given by P equals minus 10 to the minus 6, X squared plus $400. Here D is a concave down quadratic function. We could show that it decreases on the interval 0, 20,000. When the demand X is 0, in this case nobody would want to buy, the unit price is $400 per unit. And when the demand X is 20,000, the unit price is 0, but probably the company will not want to sell at that price. Let's compute two things. First, the demand X when the unit price is $175, and let's repeat this with a unit price of $300. Second, the relative change of the unit price and the demand when the unit price changes from $175 to $300. To find the demand given a unit price, we need to take the demand equation and solve for the demand X in order to have X expressed as a function of P. If P is minus 10 to the minus 6 X squared plus 400, then this implies that 10 to the minus 6 X squared is 400 minus P. Multiplying on both sides by 10 to the 6, which is 1 million, gives that X squared is 1 million times 400 minus P. And taking the square root of both sides gives that X is the square root of 1 million times 400 minus P. But 1 million is a perfect square. It's 1,000 squared. So pulling 1 million outside of the square root gives that X is 1,000 square root of 400 minus P. Therefore, X is a function of P, and we can call that function F. So X is F of P. With X equals F of P in hand, we can find the demand for any unit price. Let P1 be the initial unit price. So replacing P by P1, which is $175, gives that X1 is F of 175, and that gives a demand of 15,000 textbooks. Using 300 for P2 gives a demand X2 of 10,000 textbooks. The second part of the problem asks for relative change in the unit price and the demand. Because if the increase is of $10, for textbooks it might not be too much, but if we are buying a pack of gum, that would be outrageous. That is why focusing on the relative change makes usually more sense. Now, the relative change in the unit price is obtained by comparing the change of the unit price, delta P, to the initial price P1 of $175 per unit. This gives P2 minus P1 divided by P1, which is 300 minus 175, or 175, and that equals to 5 over 7, or approximately 71%. The relative change in the demand is obtained the same way by computing x2 minus x1 over x1, so 10,000 minus 15,000 over 15,000, which is minus a third, or approximately minus 33%. Finally, the interpretation is that when the unit price changes from $175 to $300, it increases by 71%, while demand decreases by 33%. The concept of elasticity of demand comes from the result obtained by comparing the relative changes of demand over the unit price. We therefore want to compute delta x over x1 and divide it by delta p over p1. This gives, in our example, minus a third divided by 5/7 or minus 7 over 15, which gives approximately minus 0.47. We can write this number as minus 0.47% over 1%. This way we can interpret that number as the percentage change of demand over the percentage change of the unit price, setting this last percentage to 1. Here the interpretation is that when the unit price of the textbook changes from $175 to $300, an increase of 1% of your unit price gives approximately a decrease of 0.47% of the demand. So far, we have looked at how demand changes when the unit price changes between two values of the unit price, or on an interval if you prefer. This is sort of like calculating the average rate of change of a quantity on an interval. But we would like to have an idea of how demand changes when the unit price changes at a single value of the unit price. That's more like calculating some instantaneous rate of change. This is where limits and derivatives will come into play, and this is where we're going to use calculus. So the problem is to find, given a unit price P, how demand would be affected instantaneously if the unit price would increase by 1%. To find how the percentage change of the demand will change instantaneously, we let the unit price change from its current value of P to a value of P plus H, where H is small. Then we will investigate what happens if we let H approach 0. Now, since the demand X is a function of P, that we call f of P, then when P changes from P to P plus H, X changes from f of P to f of P plus H. So we get that the change in P, delta P, is H, and the change in X, delta X, is f of P plus H minus f of P. If we again compare the relative changes in X and P, we obtain the following complex fraction. To write it as a simple fraction, we see that dividing by H over P is the same as multiplying by P over H. Then we reorganize the expression obtained by having H divide f of P plus H minus f of P. You may now recognize in f of P plus H minus f of P over H the expression that appears when we want to compute the derivative of f of P. Since we want to know what happens when P varies by a small quantity, we take the limit of this expression as H approaches 0. Therefore, the first factor becomes the derivative f prime P, and the relative change in demand over the relative change in unit price is easily computed by the ratio f prime of P times P over f of P. Economists define as the elasticity of demand the negative of the previous quantity. So the elasticity of demand labeled E of P for unit price of P is defined as minus f prime of P times P over f of P. Because the demand function is decreasing, the function f of P will also be decreasing, and its derivative will always be negative. Therefore, minus f prime of P will be a positive number, and P and f of P represent unit price and demand, and are also positive quantities. Overall, this makes the elasticity of demand a positive quantity itself. It ultimately represents a percentage decrease of the demand. I guess economists added the negative sign in the definition to avoid having to work with negative percentages. Finally, I would like to show you how a typical problem is solved using elasticity of demand. That would basically be what you would have to do to solve a textbook or an exam question. So assuming we're still working with the same demand function as before, what is the percentage change in demand when price increases by 1% when the unit price is $175? This is a question that asks us to compare percentage or relative change in demand to percentage change of the unit price. The elasticity of demand does that precisely, and we apply the definition. We need to compute the elasticity of demand for P equals 175, so E of 175, and that is equal, according to the definition, to F prime of 175 times 175 divided by F of 175. We first need to evaluate F of 175 and F prime of 175. You will recall that F of P was obtained by solving the demand equation for X, and we obtain F of P as 1,000 times the square root of 400 minus P. So F of 175 is equal to 1,000 times the square root of 400 minus 175, and that's equal to 15,000 textbooks. Now the derivative of F of P is best obtained by changing the square root to a power function. So F of P is 1,000 times 400 minus P to the power 1/2. And then we apply the chain rule version of power rule to get the derivative. Therefore, it gives 1,000 times 1/2 times 400 minus P to the minus 1/2 times the derivative of the inner function, 400 minus P, and that's minus 1. Since a power of minus 1/2 is like dividing by a square root, we get a derivative of minus 500 over the square root of 400 minus P. Replacing P by 175 gives that F prime of 175 is equal to minus 500 over 15. We plug and chug these values into the expression for the elasticity of demand at P equals 175, and we get 7 over 18, or approximately 0.39. Thinking about this number as a ratio of 0.39% over 1%, and remembering that the elasticity of demand computes a ratio of percentage changes of demand over unit price, we get the following interpretation. When the unit price of the textbook is $175, an increase of 1% of the unit price gives a decrease of 0.39% of the demand. Remember that this gives us an instantaneous representation of what happens for a single value of the unit price, here $175 per unit. The percentage change of demand would differ at a different value of the unit price. In the next video, we look into how we can maximize profit using elasticity of demand. Also, we see how elasticity of demand might help a business to decide at what value it should set the selling price of its products.